In this video lesson, we're going to talk about the form of reasoning and argumentation focused on in this course, which is deduction. Deductive reasoning is arguably the only type of reasoning unique to humans, and in this class we're going to look at deduction through the very formal lens of symbolized logic. Before we get into how to structure symbolized analysis of deductive reasoning, we need to talk about what it is more generally, what kinds of claims can be used in deductive reasoning, and how to assess them. Deduction is the process of analyzing the concepts and relationships between some claims that we're going to call premises to argue that they prove some new claim about that same subject matter. And here we're using prove in a strong technical sense. That means if the premises are true, it's not possible for the conclusion to be false. This property is called truth preservation. In a good deductive argument, it's impossible to start with true premises and get a faulty conclusion. And we'll get into what makes a deductive argument good or bad in the next video. So truth preservation is a unique strength of deductive reasoning when compared with other forms of reasoning. For instance, induction is the process of reasoning from a particular set of evidence or experiences to a general conclusion that applies to other similar cases we have not experienced, often predictions about the future. Inductive reasoning is the cornerstone of most sciences. It's incredibly useful and important. However, induction is not truth-preserving. This means it's possible to have a strong deductive argument with good, accurate, factual evidence and still generate a faulty conclusion. So one example of this, just to kind of drive the point home, because I think a lot of people hesitate to question this, that's often cited in philosophy of science is the example of white swans. So prior to mass exploration, right, before people moved around a lot, a scientist studying swans in Europe would say that all swans are white. Every swan they ever would have seen or studied would have been white. So induction would allow them to generalize to the claim that every swan is white, swans are only white. And this would be a good, strong inductive argument, right? They have all of the evidence, they have the expertise. However, that conclusion would be false. There are black swans that are native to Australia that a historical European scientist could not have possibly known existed. And while this is a silly example, this is a systemic problem with induction. There's no guarantee that reasoning from true evidence will generate a true conclusion. These conclusions are always open to counterexample, and that's a cornerstone in science as well, is that you have to be open to counter evidence. So where induction uses pieces of evidence that can be, confirmed or denied, deduction instead appeals to premises or claims. These claims must either be true or false. Now, deduction still has the issue that we might think a premise is true and it turns out that premise is false, but that then makes the argument bad because it has a false premise, unlike in the induction example. So in other words, every statement that we use, everything we use in deductive reasoning must be a truth functional statement. And in a good argument, they'll be true. But before we get into assessing truth, let's just talk about what truth functional statements are. So in English composition terminology, truth functional statements are declarative statements. They make some declaration or claim that describes the way something is in the world. So things like questions and commands are not truth functional. Questions are a request for information. They don't make any statement or description about the way the world is. And similarly, commands demand that something change, right? Move or bring that here. Neither of those are making any claim about the way the world is. They're demanding something change or act a certain way. So it doesn't make sense to ask if things like questions or commands are true or false. So now let's go the other way, and I want to clarify that by truth functional, we don't mean anything like the popular understanding of opinion versus facts, right? Opinions also make claims about the way the world is. For example, the claim that chocolate is the best flavor of ice cream is still a descriptive claim that chocolate is better or tastier than all other ice cream flavors. So while we might say it's a subjective claim or something like that, it would still make sense for me to ask you whether it is true or false that chocolate is the best flavor of ice cream. So this is still a truth functional claim, and most of the things we consider opinions are still going to be truth functional in this way. The other class of truth functional claims that might not seem to be things that we might consider are truth functional claims that have unknown or unknowable truth values. For example, the claim God exists is truth functional. It's either true or false, even though it may be impossible to know for certain or to get people to agree whether it's true or not. Now, claims like this you might not want to use in a real actual argument against people, right? Because they'll refute your premise, they'll argue against the premise, but those are still truth functional statements. So now that we know we're working with truth functional statements, we need to get into how to assess them. There are two different levels at which we can assess the status of truth functional statements. The first is the statement's actual truth value. To do this, we have to look at the relevant facts and determine whether the statement is true or false. This is the notion of truth and falsity you're already familiar with. For example, the statement, "My name is Ellie," is true when said by me, and we abbreviate that it is actually true by saying that it has the truth value of T. The statement, "FSU is in Gainesville," is false of the actual world, right? We know that FSU is in Tallahassee and UF is in Gainesville, so it has the truth value F. The second way that we evaluate the truth value of statements is their logical truth value. And this doesn't have to do with the actual content of the sentence in the actual world at all. Instead, we look at the structure of the sentence. Here are some examples, and we'll get into how to assess them more deeply in a minute. So, "It is raining" is logically indeterminate. Nothing in the structure of this sentence tells us whether it's true or false. We'd have to look outside the window. So a logically true statement is "it is raining" or "it is not raining." If we look at the structure of the sentence, we have a claim, "it is raining," and the negation of the claim, "it is not raining," connected by the "or," which we call a disjunction. And logically, it's not false. It's not possible for the sentence to be false because either the claim or its negation is going to be true, right? We don't have to look out the window to know that it's either going to be raining or it's going to be not raining. That just fits in the structure of the sentence. We know that that sentence is going to be true. And so our last example is a logically false sentence. So this is "it is raining and it is not raining," which claims that something both is and is not happening at the same time, right? We don't have to know anything about rain or weather or have any windows to know logically that this is false. So now let's get a little bit deeper to talk about these logical properties in their technical aspects. So when we're talking about logical properties, we're normally looking at the possible truth value of a sentence or set of sentences, focusing more on that structure, right? So when it comes to logical truth value, we're looking at whether it's even possible for a given sentence to be true or false structurally, not talking about whether it's actually true or false in the world. The technical definition of logical truth is a sentence is logically true if and only if, which you'll see abbreviated as IFF, it is impossible for it to be false. So think back to our example on the last slide. "It is raining" or "it is not raining." Logically, it's not possible for this sentence to be false because either the claim that it is raining will be true or its negation that it's not raining will be true. One of the two have to be true. It can't be true that it's neither raining nor not raining. So next, logical falsity. A sentence is logically false if and only if it is impossible for it to be true. This is exactly what we already said about "it is raining" and "it is not raining." It's not possible for both of those statements to be true at the same time, which is what we would need for the conjunction with the "and" to be true. Last, let's look at the definition of logical indeterminacy. A sentence is logically indeterminate if and only if it is neither logically true nor logically false. Another way to state this definition is that it's possible for the sentence to be false and it's possible for the sentence to be true. Our example, "it is raining," is exactly this type of statement. Without actually looking at the weather, It's possible that this is true and possible that this is false. A quick reminder, a statement being logically indeterminate does not mean that we do not know its actual truth value or that it isn't useful, right? It is raining. We can check and know its actual truth value fairly easily, but it's still logically indeterminate. And most of the statements we use in real arguments are logically indeterminate. Logically false statements are usually obviously contradictory, and logically true ones are often trivial and seem useless for actual reasoning, like the examples, it is raining or it is not raining, or the example, everything is or is not a potato, right? True, but not helpful for anything. So now that we've gotten the properties of individual sentences, their actual values, and their logical truth values out of the way, let's look at some logical properties of sets of sentences. So first we have logical equivalence. A pair of sentences are logically equivalent if and only if it is impossible for one to be true while the other is false. Logically equivalent sentences always have the same truth value. So this is a pretty trivial example. Cupcake is a dog and sugar is a dog as the first statement, and sugar is a dog and cupcake is a dog, the second statement, are logically equivalent. Both statements will be true if sugar and cupcake are both dogs, and they'll both be false if either cupcake or sugar or both are not dogs. So while these two are very similar, definitely be careful not to say that they are the same statement. The changing of the position of the components of a sentence isn't really important in this case with a conjunction, but it does make them distinct statements, right? So these are logically equivalent, but they're not the same statement. So next we've got logical consistency. And a set of sentences are logically consistent if and only if it is possible for all of the sentences to be true at the same time. And remember here, we're talking about possibility, not whether or not the sentences are actually true. So cupcake is a dog and cupcake is fluffy are logically consistent because it's possible for something to be a dog and fluffy. And they're logically consistent even if it turns out that cupcake is a hairless cat. Cupcake is a dog and cupcake is a cat are logically inconsistent, right? Because they can't be true at the same time, as long as we acknowledge, the implicit claim there that it's impossible for anything to be both a dog and a cat at the same time, or that a dog can't be a cat. So the definition of logical inconsistency is just that they're not logically consistent. In other words, that it's impossible for all of the sentences in a set to be true at the same time. The last property we're going to look at in this video is logical entailment. And this property captures the nature of deductive reasoning as truth-preserving. A set of sentences logically entails a sentence if and only if it is impossible for all of the members of the set to be true and that sentence to be false at the same time, right? So all of the members of the set true and that sentence false at the same time on the same possible truth values. So here's a really simple example. The pair of sentences, sugar is a dog and cupcake is a dog, logically entail the sentence, sugar and cupcake are both dogs. If both of the first two sentences are true, it's not possible for the third sentence, which conjoins them, to be false. Entailment is incredibly similar to validity, which is a property of arguments we're going to focus on in the next video. You don't really need to understand the nuances of the differences between them, but just remember that validity is a special case of entailment that applies specifically to arguments, and entailment applies much more broadly. If you're confused on this and want to learn more about that distinction, check out page 11 of the logic book, which you should have available to you on Canvas. So now we need to talk about some special cases of these properties and the ways that they relate to each other. It's important that you understand how and why each of these special cases work. So first, every logically true sentence is entailed by every set of sentences, including the empty set. And by empty set, I mean a set containing no sentences at all. So a logically true sentence is entailed by everything and even by nothing. And this is because the definition of entailment specifies that it is impossible for a set of sentences to be true and the entailed sentence to be false at the same time. Because it's already impossible for the logically true sentence to be false all on its own, right? So it satisfies that definition of entailment regardless of what the sentences in the set are. Just one more time really quick. If the entailed sentence can't be false, then it can't be the case that the entailed sentence and the entailing set, that the entailed sentence can be false and the entailing set can be true at the same time, right? Because that entailed sentence is never going to be false. So for logically true sentences, they're entailed by everything. So next, all logically true sentences are equivalent with each other. Any two logically true sentences satisfy that definition of equivalence I gave you on slide 7, that it's impossible for one sentence to be true and the other sentence to be false at the same time. And this is because it's always impossible for a logically true sentence to be false. All logically true sentences have the same truth values. They're always true. Relatedly, all logically false sentences are equivalent, and the reasoning here is the same, right? It's impossible for a logically false sentence to be true, so any two logically false sentences will satisfy that definition of equivalence, that it's impossible for one to be true and the other to be false at the same time, because they're both always going to be false. They have the same truth values. And just a note here, this doesn't carry over to logically indeterminate sentences. Logically indeterminate sentences are not always equivalent to each other. Here's an example. Sugar is a dog and sugar is a cat are both logically indeterminate sentences, right? You would have to meet the animal sugar to determine whether sugar is a dog or a cat or something else, but those are obviously not logically equivalent, right? If sugar is a dog, then sugar is a dog is true and sugar is a cat is false. So it is possible for them to have different truth values at the same time. They're not logically equivalent. And the last special case we're going to talk about here is that any set containing a logically false sentence is an inconsistent set. Remember, the definition of logical consistency is that it's possible for all of the sentences in the set to be true at the same time. If you have a sentence in the set that's logically false, it's already impossible for that sentence to be true no matter what. So it's impossible for every sentence in the set, including the logically false one, to be true at the same time. So if you have a logically false sentence, you have an inconsistent set, no matter what else is in that set. In the next video, we're going to be covering using the basics we covered here to get into the technical details of deductive arguments, which will be the focus of this course going forward. In class, we'll be covering the material for both videos together, so I recommend you go ahead and watch that one soon while the information from this video is still fresh in your mind.